this question that asks to play with a Java, with a GeoGebra app and do various things with this. Just if it didn't happen in this class, then I'm not sure how frequent it was in this class. In the other one, I saw it quite frequently that you had here the vitamins. How do I make it a bit larger? So you have, if you remember, the various types of vitamins. In this question, you can ask, where are in my diet all the vitamins where I'm getting exactly what I need from vitamin A, and they are all along this line. All the diets that I'm getting at least enough vitamin A, and they are all the diets in this part of the shape. All the diets that you're getting enough vitamin A, B, C, D, and then you're getting this convex region with a few vertices on it that I wouldn't spend the time to make the font fit right now, but if you remember, there are several vitamins. Over here, a few vertices over here, each one is the intersection of two of the limited vitamins, and then I asked what should be the ratio of prices, so vitamin A, ratio of prices, so let's say the first vitamin, give me a second, I'll try to do something with this. So, yeah, I'm sure. What should I do? So this vitamin will be the cheapest, will be the most economical one. Under which prices? And sometimes I get as an answer, I'm telling you if you didn't do this mistake, sometimes I get as an answer that this will be the coordinates of a vertex, but question was about what should be the ratio between. The question would be what should be the cost, which is essentially what should be the ratio of the cost, only cared for the ratio, between the cost of banana versus vitamin, so that for some budget, this will be the cheapest diet. I'm slowly increasing the diet, and if I played well enough with these two costs of the cost of banana versus cost of oranges, that once you're playing with this cost, actually you care only about the ratio of this cost because this determines the slope of this half plane, slope of this line, and as this half line moves parallel to itself and you're changing the budget, at some point you'll hit the cheapest diet that is still healthy. So if you said, so it was some confusion that I wanted to talk also to you about it. Questions about homework? What do we have now? 3 that is approaching. 1, 2, 3, yes.
I haven't checked today, so I apologize. Have you opened the grade scope turning thing for it yet?
Yeah, of course. And we need to think, I might miss some piece of technology about how to do it properly in Gradescope, but at the moment, unless I'll figure it out. If you're working in a pair, then one person will submit the pair, and the other person will just submit a page saying all the question, take the grade from this other person. Okay, so only one person needs to submit, the other one can submit an empty PDF, just say on the PDF, my partner is X. The hashing is included. I said you don't need the hashing questions are included. I mean, the hashing part is included for homework 3, yes. I had only 3 questions about hashing, and you are, if you read the facts before it, then you're completely capable of answering the hashing questions. They did not get very much technical. I'm usually not very strict about deadlines, but it's not a clear cut here that the question about the hashing, people asked me on Piazza, I'll check, I'll think about it. The answer is probably yes, but it's not because of the hashing question. It's because I'm not very much into, I said it many times, that unless I have some very good reasons to be strict about deadlines, I cared what you submit, much less about when do you submit it. So that's my, yeah.
So in question 7, the last paragraph talks about MD5. So is it related?
Is this in question 7? So I didn't comment it. Okay. So maybe there is a typo. I'll double check it. Thanks. I thought somebody was answering a commented out text. Somebody was reading the LaTeX instead of reading the PDF. But if it appears in the PDF, I will not check it online. But I'll tell you right after the class. Okay, let's do hashing, if there are no other questions. Let's do hashing. Most of you have seen hashing in previous courses. The hashing that I'm teaching is not the same. We are going to see much, much more material. But to cover whatever we are also covering in 445, in all our data structures, hashing included, we think about items of data that consist of a key and consist of auxiliary data, satellite data, like student ID versus student name, student record, and so on. Okay. So and we want to perform insert, delete, and search, find, using the key. And we want to organize this data in various ways. Hopefully, you can always use skip list or various binary search trees, but hashing are significantly faster. And I've taught hashing numerous times in various levels, really numerous times. I'll try to pay more attention to things that I know that are confusing. And the notation is the first one in the list of confusing parts. The universe are all the possible keys that might appear to our specific application. Okay, universe is just a huge set of, say, if our key will be, determined by the key, but if our key is student ID and it has 16 digits, then every number with 16 digits is in the universe. So it has 10 to the 16, many units. In the universe, what rule is the universe plays for us? Well, it helps us narrow down the hash function that is willing not to crash, to take any key in the universe, any student ID, and it shouldn't crash. It should do something with this key. Hash function takes every key in the universe and spits out a number between 0 and m minus 1. M will, if we are thinking about data storage application, m will be the number of cells. M will be the number of cells, and m is used only in this context. I'll play from time to time with this cubby that is good approximation to a hash table where I have 8 cells out there in the cubby, and I'll put things in cells of the cubby. And this is just an analogy to hash table where we'll store keys. So inside the set of inside the universe, there are the sets of keys that we need to store right now. These are the students at the university. That's the ones that we need to store their record. This is a set capital K. Of course, it's not proportional. K is much, much, much smaller than the set of the universe. These are the keys that I need to store. And the trick, what hash function helps us to do, is to assign for every key a cell of the cubby where we are going to store this key. So K1 go to this cell, whatever its index. So age of K1 is just the index of this cell. That's where I'm going to store it. Age of K2, it's the index of this cell. Age of K3, get, again, just the index. That's where it's going to be stored. And that also means that if I'm going to perform a find of K1, that's where I'm going to search for find. Maybe I'll be successful, maybe not. But my first attempt to find K1 will be exactly based on the hash table. Stories that I like to tell. Udi Manber used to be a faculty at this department until 1999. Then he got an offer from Yahoo to be the chief scientist, because at this point he was one world expert in search engine, and they definitely wanted to have his expertise. So he became a chief scientist at Yahoo, moved to be, I think, a vice president in Amazon, moved to be chief algorithmic involved in research on Yahoo and YouTube at Google right now, last time I heard from him. And very, very successful guy, did not come back to the department, unfortunately. Very, very appreciated person. After being in so many high ranks, I heard him giving two invited talks, one in a big conference. He gave an hour talk, and somebody asked him, what is the most important data structures that we need to teach our students? And he said, hashing. So let's put enough important on it. That's the most important data structure. And then he gave a lecture here a few years after. And I asked him if he still stands behind the same answer that hashing is the most data structure. And he said, yes, hashing and maybe Bloom filters as well. So we'll also talk about Bloom filter for him. That is a derivative of hashing. Okay, Bloom filters. Check it out. Okay, staying with hashing. Everybody understand what is hashing so far. Age tells us where we are going to look for the key. And the problems will happen, of course, in the case where you have in K two keys that are all mapped to the same cell. We have different strategies of how do we handle the case of collisions. But the whole deal about hashing is in collisions. And you can ask, can we have a hashing that has no collision at all? So in a perfect hashing, the answer is that yes and no, depending if you are in 445 or 545. In 445, the answer is no. In 545, the answer is that we can construct a hash function called a perfect hashing that creates no collisions. So far, looks great. What's the caveat? That we need to know K. I can design this function only after I know what are the set of keys that I'm going to store. And it will be perfect hashing. No collision means each item of data lies in its own individual cell. But it takes away one of the most attractive properties of the hash table, that I can decide what is a hash function before students start to arrive, and it's just very likely to work even if I don't know who are the students. Here I need to know who are the students, what is K that I'm actually going to store. It's not enough to know that it's going to be a student ID that will be the key. I need to know what are these keys. Okay. So we are going to spend some time talking about handling collisions. I'll show you two that appears in CLRS. At some point, I'll leave CLRS and discuss cuckoo hashing that are more modern and different type of solutions. So one type of solutions will use chain hashing. Conceptually, it's the simplest one. Practicality, it's much less popular. We just said if you have a few keys that are all mapped into cell I, say 49, 86, 52, are all mapped into cell I. I have, of course, collision. I'll store them in a linked list. And if another key will appear and I want to be entering to this list, into cell I, I'll add this key into this cell. And if I want to find the key, I need to pass over all the keys, but only in this cell, because the hash function, our big assumption about the hash function is that age of k could be computed in order 1 time. We're not very interested in hash functions that are not constant time. At least something that doesn't depend on n. So to insert a key into a chain function, if I resolve collision by using linked list, how much time insertion takes? It's not a very well-defined question because I didn't discuss everything, but insertion takes yeah. So it's depending if I'm making sure to find the key before the insertion. If I'm sure that it's a key that is not in, you're both right. If I'm sure that it's a key that is not in the table, then I can insert it at the beginning of the list, always. It didn't say that I keep it sorted. So I can insert in constant time, no matter how long this list is. But find or delete means go to this list. And then the time is to go to this list to find the first element takes a constant time based on this assumption, but then to find it in the list depending on how long this list is. Good. So some analysis of chaining, it's mostly warm-up. Alpha. OK, every time when we are talking about hashing, n is a number of keys in the table. Keys in the set of students there, not in the universe at all. M is a number of slots in the table. Alpha is just the ratio between them. How many keys divided by slot. Okay, and we'll use the same notations throughout the whole chapter. Okay, so as long as this number is small, number of slots and the number of keys is roughly the same, then the and the goal of randomness works for us. We pick the right hash function. Then the expected time for a search would be 1 plus how many keys do you have on average? How many keys do I have on average divided by how many slots do I have on average. So in some sense, it's a constant. Right? Because I need to check for the key. If I average over all the keys, then maybe I need to check for a key in this list. What's the average time to find a key in a linked list if all orders are equally likely? You can be slightly more accurate. The average time to find a key in a list that contains, say, R many keys. R over 2. Because of symmetry, the chance that it is the first one is equal to the chance that it is the last one. The chance that it is the second from the beginning is the same chance as it's a second from the end. They cancel each other. So the average, when you sum them up, or you're saying, maybe it's this one, so it takes 1 time, 2 times, 3 times, 4, 5. Let's sum them up and divide by 2. So you are getting that average time either way is n². And then you are summing them up, and that's the average search time. Why does this number comes from? Where this number comes from? The one is because even if you're searching for somebody that doesn't appear in the hash, you're still spending a constant time, no matter how many keys you have. Something is strange in our recording. Give me a sec. Yeah. Okay, so the expected search time is constant if alpha is a constant. But of course, the search time could be n squared. The expected search could be order n if you're looking for the last element, and it is in the very last cell. To get this assumption, to get all this running time, you need to have the property that every key is equally likely to be in cell 1 or in cell 2 or in cell 3, all the way up to cell m minus 1. Every key has exactly the same chance to be in each one of the cells. But obviously, if all the keys appears in the same cell, then you're not appears in a single cell, then you cannot argue that the search time is constant. I hope everybody sees it. Okay. What does it mean practically about hash table? What should be? I generate a hash table. If you're using Java, maybe you don't care that much about what we are going to say, because in Java you can say, I'll always add more cells to the table, and its size is, as far as I care as a user, its size is, can be dynamically increased. If you care about performances, then there are many reasons that we like array much more than we like linked list. Many, many, many reasons that arrays are so much better than linked list. So let's say arrays versus linked list and other dynamic memory. Dynamic memory allocation, which means that what we are doing, let's say in C, would be I'll ask for a piece of the memory of the table. I'll ask for a block with 10, 24 many cells of specific type, and that's my block from now on. And I'll put the hash table in this block, and my access to this array is much faster. Okay, and it will sit contiguous in memory. And there are a lot and lot of pluses of why you prefer to use arrays versus anything with dynamically memory allocation. Dynamic memory allocation might be linked list, but it might be also dynamic arrays that you're using, or things that happens underneath the hood, that some memory reorganization happens without you careful. So it allows you much faster access time. There is no auxiliary data structures that you need to find to see where every piece in the memory is. And it also works for better paging, more efficient paging. You know, paging meaning you ran out of memory on your main, you ran out of space on your main memory, so some parts are mapped to slower memory units, stored in the memory unit. If you remember, you don't hear this noise so much, but if you remember, you ran a big program on a slightly older disk drive that used hard drive. Then the running time at some point, you started to do paging, and then you started to hear in the background the of the head of the hard drive, bringing things back and forth from the memory, which you still need to do even once you're using more memory than you had on the fastest hierarchy of the cache. Of course, there is always some paging, but it works much better if once it either brings the whole array back and forth to the main memory as a whole, rather than bringing lots of pieces. That's the whole notion of paging, as well as verification. As well as shared memory, as well as if you want to use GPU GPU or parallel, all these things work so much better if there are clear memories that you have control over their sizes. And your program will run much faster. So that's a very general discussion to steer you away from linked list. But it also have an implication about hash function and hash table. Right? We want the hash table to be a contiguous piece of memory. So what should be the size of the hash table? If we don't know how many keys are going to store in the hash table, and keys are just going to appear. Two possible answers. If that's the only table that you are using in your program, take the maximum size of a hash table, you don't lose on it. If this hash table is one out of many other pieces that might need to grow, and they are all in your hash, all in your memory, and you are not sure which one will need a lot of memory and which one is not, then it brings us back to the dynamic memory, dynamic arrays from homework 1. Decide about some size, and one its field, not necessarily one key after the other, but keys will be in different locations. And once alpha is becoming too large, alpha, remember, number of keys divided by number of slots. Once you see that you inserted too many keys, you'll notice that the hash table start degrading, and that the performances start degrading. That's a good hint to double the size of the table. And the other way around, when you are decreasing it and the table starts to be too empty, and if you need the memories, then you have the schemes of the dynamic array from there. OK. Let's talk about criteria to choose a hash table. So for a while, I'll assume that the keys themselves are just numbers. But very soon, we will leave this assumption and say keys can be geometric shapes. I want to hash images. I want to see if somebody's using any of my copyright images. I want to hash music. I want to hash a text of legal documents, and so on and so forth. So most keys are not just numbers, but now in the discussion, let's assume that it's just a number. The criteria will still be the same. If I have two keys that are different, K1 is different than K2, no matter in which bit they are different. If the first bit, the last bit, no matter how did you write it, as long as they are different, age of K1 should hopefully, I cannot guarantee it, obviously. One of the homework questions says why you cannot guarantee it. There will be a lot of keys, no matter how you picked your hash function. You'll find plenty of keys that wants to be mapped into the same cell. Hopefully not all of them are students that you actually need to store, but there is always many more keys than the number of cells. So I cannot guarantee it, but I want to at least to maximize the chances that two keys are, if they are different, then they are mapped to different locations. And that already suggests a few things that you probably don't want to do. Let's say here is K1, which would be 1, 2, 3, 4, 6, 6, 7, and K2, which would be 1, 2, 3, 4, 6, 6, 8. And just student ideas, student ID that of two students that one came after the other. If my hash function is K mod 100, and that's how the student ID looks like, that is just each one got the next number in the sequence order, then what does the function K mod 100? And we'll see lots and lots of mod operations today in the next meetings. what does mod do to the structure? Mod of 100. Just look at these 2 digits. Is this good or is this bad? It has advantages. In this case, it's not too bad, but definitely doesn't satisfy this assumption of any changes of the bits will cause a different hash function. Like, if that's a hash function that I use, I don't pay any attention to what's happening to the right of these 2 digits. So if I'm always adding a parity bit or adding some other digit over here that generate at which department you are, here is a department number, then of course it's a bad idea. So in practically, mod is a great function. We like mod in some cases, but it's very easy to compute. But be aware that you are not missing big chunks of possible differences. Trivia questions, if you didn't take hashing with me before, what does hashing mean in English? Outside computer science. Where did you hear it outside computer science?
Google, it means slime thing into small bits.
Yeah, in hash brownies. You're taking a piece of meat, tofu, slice. I'm vegetarian, come on. Slice. This way slices. This way destroy all the structures that you already had, which is exactly what we want the hashing to do. We want to scramble it and to split it so everything is like uniform or like random. That is, if I had one big, I guess in the piece of the meat/tofu that you used, if you had one good region and one bad one, then after the hashing, you want everything to be scrambled. And that's exactly what we want from the hashing to do. OK. If you're OK with the idea of mode, using the mode, then mode 100, well, people like it very much. Like, if you think, and it takes, as we said, only the right 2 digits. What about k mod 10 to the 10th? But now we are thinking about a binary number, and this operation, take k mod 10th, just look at the 10 rightmost binary numbers. And computers like it. How do you implement it? The fastest implementation that you can think of. Sure, you can use a mod operation directly, but you can do faster if you are. Yeah. You are either masking it. You can do bitwise and. So there will be masking coming up later, so not one, but you're doing bitwise with 1, 1, 1, 1, 1, 1 with 10, a mask of 10 ones, 10 ones, and the all is 0. And what happened to these ones is that the first 10 stays the same. Everything to the left is becoming a 0 if you're doing bitwise mask. OK, so sometimes it's called the division operations. What's good? Let's think about another operation, another cases that might appear in the data, and this function will happen, will not be great. Let's say that I am using m equal 10. That would be my hash function. That would be the m is the size of the table. And let's say that k, the set of keys, would be 100, 105, 106, 105, 110, 115, 120, and so on. What happened to my hash function when I'm using these keys and m equal 10? You see what a property, right? I'm just adding 5 at each iteration, which in the table itself, it will mean that cell number 0, who is mapped to it, this one and this one and this one are all mapped to this cell. This one and this one are all mapped into cell 5, and nothing is mapped to the other cells. And it's not that surprising that you will use the last digit for validation or some jump. And it's just the case that something in the data suggests that the jumps are by values of 10 or values of 5, or anything that is related to m, the size of the table. So if you're just doing m, then it's safer to think about m, which doesn't have a small divisor. M that doesn't have a small divisor. For example, M that is even suggests problems if the jumps in the data are jumps of 2. You maybe hit only the odd cells or only the even cells. And you will not store in other cells. So better to have M that is not even, but then our computer likes us less because the computer does like to have pieces of memory that are a power of 2. Computer likes to work with blocks that are of size 2, 4, 8, and so on. So it's a bit contradict each other. The same goes for if m is 3 times something, has 3 as a divisor. So if you want to play it safe in this aspect, you know, there are numbers that don't have a lot of divisors. Namely, take m to be prime, and then you are kind of secured in this aspect. And luckily for us, there are infinitely many primes. Otherwise, it would be much harder to do cryptography. So you can always find prime that is around the size that you want the table to have. OK, yeah, we talked about it. That if m is 2 to the r, then we are only looking at the last r digits. OK, yeah. So sometimes making the table size a prime is inconvenient in the sense that you are wasting some memory. If it's for your desktop, it's probably not an issue. If you are programming a smart sensor, maybe it's a bit more of an issue that you are not taking advantage of all your prime. OK, getting a bit into better methods or different methods. These are quite popular methods. So what's going on here? Again, I want to give every piece of my key let's remind everybody what am I trying to get with all this exercise. Here are 2 keys, K1, which would be in binary 1, 2, in. So I skipped the key. Between these two keys are different. They have the same number of digits. What am I trying to get by all these methods? I want to say, as long as there is any difference in any digit between these 2 keys, I want to increase the chances that they are going to different places. And the first obvious conclusion of this, want to look at the whole key, is to say you cannot have any part of the key that doesn't affect the hash table. You cannot have any part of the key that does not have any impact on the hash table. If I look at the first digit or the last digit or the middle digit and change, increment, decrement, any of them, it should affect what is age of k. Age of k should hopefully change no matter which digit I change. Right? There are no ignored digits. Everybody understands me so far? I think this might be a bit of an obscure part. As in contrast, a hash function that do only the modulo looks only on the last two digits, if it's modulo 10 or modulo 100 or modulo 1000. And that's in representation of when they are represented as decimal numbers. And it's not any better if I think about them as binary number. And I'm doing modulo of 2 to the k. Mod 2 to the k just looks at the k last digits. Again, I'm missing the point. So how can I don't want to pay too much attention, to waste too much time on each digit individually, but I still want something that will take all of them into account. And again, I'm under the assumption that k is just an integer or at least a number, but not a string. We will talk about string later. How do we hash strings or very long text? Here, k is a number. And I pick a as a constant, and I want this constant to have a lot of digits. Lots and lots of digits after the decimal point. So k, and hopefully these numbers appeared in what looks like a random option. I'm not using a random generator here, but I don't want the digits of a to be nicely correlated with each other. For example, 1, 2, 1, 2, 1, 2, 1, 2, 1. 1, 2 is probably a bad one. Square root 2 is a good such constant. Now, what do? I take k and multiply it by a, this number that I keep in mind. Of course, I don't forget this number because once I'm searching for a key, I'll use the very same hash function. I need to know what is a. Look at a times k minus a times k floor. Let's take an example. AK equal 32 minus dot 54. What's happening here? I'm taking a times k minus a k floor. What is left out of here? 32 minus the floor of 32 times 54. You're getting at the end 0.54. Only the float part of a times k is left. Right? This expression means that you are left with only what comes after, only with what comes as a value between 0 and 1. So this will be somewhere between 0 and 1. And the nice thing is that if you think about, here is k. Here is k as a number. So I'll make sure it's this times dot 0 times square root 2, which would be 1.4141414213, yada yada. Lots of digits here. And now when I'm doing the multiplication, then this summation takes into account this times this, and this times this, and this times this, and this times this. All these functions appeared all together, and they all contribute to it. All digits participate. Right? And I don't necessarily say that it's very important what happens at the very left of k, or that it's very important what happens to the very right of k. All the digits of k will participate when I multiply these two parts and take the float number. So the float number, or the actually, what's called modulo 1 of this number is just what's left to the right of the decimal point. So it's between 0 and 1. And now I need to make a number between 0 and m. I need it to be an index of my table. So I multiply it by m. It was between 0 and 1. Now it's between 0 and m. Less than m, larger than 0, but not a float number. And I need it to be an index, so I do floor once again. And that's my hash function. And that's very popular. All good? Everybody understand what's the motivation behind it, how we are taking into account all the digits, in the sense that if I'll change one of the digits, there is a good chance that my solution will change. Now, it's a good point to mention how random generators works. How the random number generator works in applications. So if you really need random value, then you are looking at some physical property of something. Like there are military jammers that are built to create noise to either disturb your communication or protect your communication against enemy listening to it. And where you really need randomness, then there are sensors that look at the patterns of the smoke they sit on trucks, these jammers, pretty loud thing that sits on trucks, and there is little camera that look at smoke coming from this generator and identify patterns in the smoke, and that's randomly is enough, let's say, in the sense that it's very hard to predict what will be the next number. If we are looking at what we are usually using in our computer, it will be pseudo random generators that for most applications are good enough. And for this, you are taking the seed as a first number. That's why you are asked to prevent the seed. And the seed would be the first number, A0. And next, you look at hash function that looks quite similar to this one. You just don't need to multiply it by m. And you're setting A1 to be the hash function of A0. And A2, the next time that you are calling the hash function, it remember what was the result in the previous call and applies the hash function on the previous call. And in general, each time that you are calling the hash, that you are asking for the random number, then AI will be the hash function of A of I minus 1, the previous value that you generated. So this has lots of great values, like that, or if you're asking for all these numbers to be between 0 and 1, then the average of a lot of these numbers would be half, which is like, obviously. That is, that half of these numbers will be smaller than 1, half of the number will be larger than 1. The statistic will be, for most cases, just if you used real random values. But obviously, if you are setting the seed, once again, you set the seed to the same numbers, and you'll get the same sequence of numbers, once again, for good and for bad.
I have a question. So is the outer word floor function in the hash gonna make it more likely to get a collision?
You're talking about why do I use this one?
No, I mean, yes. I mean, the outer word floor function gonna make it more easier to get some collision, right?
I mean, here I'm using it for storing things in the table. It must be a number between 0 and m.
The inner, I understand. The outer will make some, yeah.
This one just make it an integer.
Yeah, but because we are routing it to a floor, we're gonna make some different index into mapping in the same cell, right?
Right, but let's ask what are we let's put the expectation straight. What should be my expectation? I have two keys, K1 and K2. And if I'll store my first key at cells age of K1, it's an excellent question, and it's very good discussion. Let's keep our expectations straight. I have altogether m cells in the whole table. Age of K1 is going to be stored somewhere. Hash function, that's what it does. If I take K2 and do a real hashing, a real randomness, I don't try to look at where there are keys and decide where K2 is going to be there. I'm just going to drop it randomly in each one of the keys. What's the probability if I drop it at random? What is the probability that age of K1 equals of age of K2? That there is a collision. The chance that there is a collision would be if I just drop age of K2 into a cell. The chance that it's the same cell would be, of course, 1 over m. Because K2 has no idea where K1 is. Each one of the cells has the same probability to be picked. So that's essentially what I'm getting from this part. I have to get an integer, so what's the chance that it will be the same integer? So it says this is doing quite well in the sense of it doesn't give higher chance that I'll hit only this value or higher chance that I'll hit this one. That is. And it's kind of, it's what you need to do if you don't know anything about the distribution of the data. Once you know things about the distribution of the data, maybe you can do better. OK, a bit more about sometimes it's fine to multiply a k not by a float number. A shouldn't necessarily be a float. It's a different method. Here I do take k to be an integer. Here they are in binary. I do k to be an integer, and I multiply them. But as a result, what do I need when I'm done with the computation? I need an index on the table. I'll take A to be a long number. K is a long number. The multiplication in binary is a long number, but I only pick a few digits. How many digits do I pick? As many so that I have exactly an index of the table. I'll just take, say, if my table has 8 cells, then how many digits do I need, binary digits? Do I need to index each one of the cells? Exactly 3. Right. So I'll take 3 digits. What should be these 3 digits? It's not a good idea to pick them at the very end. Why? Because then from the key, it's the highest most digits that influence what happened in the very left part. It's not a good idea to pick what happened in the beginning, because then in K, only the first digit influences what happened to the right. I'll take the 3 digits to be in the middle of the number. And how do I do it elegantly? You'll see in the next slide, but just intuition about why multiplication in general works well is this animation that will say, I'm taking the key of 1 times k. And it takes me to some point in my table. And now, so that was the value of a times 1. But remember, what does modulo mean? It means that all my keys are along this circle. And if I'll add something to it, modulo this number, I'm just continue from this point to the next point. So now I'm jumping from age of A to 2A mod 8. This was A times 1 mod 8, 2A mod 8. And I jump to some very different location that doesn't look very much connected to the first key. Not necessarily close, not necessarily far. Add 3 times A, again, jumps remember it's all modulo 8 on the circle, jumps to very different location. By the way, I think that we'll talk about locality-sensitive hashing, locality-sensitive hashing that do want that nearby points will be close to each other in the table. They are actually used for nearest neighbor in high dimensions. We'll talk about them, and that we don't want things to be sprinkled around. We actually do want some locality to be preserved, and that helps us to answer. If I have a large data set that lives in 5 dimensions, we talked about it, we have cats, dogs, straight. I have several parameters that I store, and this will tell me. OK. Here's part that doesn't appear on the book, and I insist on putting it here because I see it as one of the really important things that you can do with the hashing. So here is my problem. I'm going to store a lot of songs. And maybe they are all, at least historically, they were all being downloaded illegally. And maybe you are being pursued by some the music companies. But I'm talking about Casa in its first days. And you want to store, and there are lots of users. And the deal was that as a user, you were willing to store. If you want to be a user of Casa, you have to store a lot of songs, not necessarily that you are interested in on your hard drive. You have to contribute some data or some part of your hard drive for Casa to store whatever they want on it. It doesn't mean that you have always to be online. And this was a great idea to where hashing is used. So what do we want in general? We have a set of data items. And the same goes for if you have one RAID, but it consists of multiple disks, multiple hard drive. So it's one set of 8 hard drive, either connected on the same axis or not, but there is a chance of corruption of data. Data can go wrong in each one of them. There is a chance of unreliable. So what's my problem? I want to have some robustness. I want each item of data to be stored in more than one hard drive. If it's stored only on one hard drive, out of them, if this hard drive goes bad, I lost this data. I want to use the hard drive so I want to store it on several hard drives. Or if it's a Casa user, then this user might be offline exactly when somebody wants this song. So I want a few of the users to have it. Whom should be these users? If I'll always pick the same 3 users or the same 3 hard drives, then the other hard drives don't utilize at all. I don't store anything about them. So I want to have, in this example, every item of data to be stored on 3 of the 8 hard drives. But which 3 should it be? I want fairness. Each one should store what? If I have M songs, or M units of memory, we are using M. I have F. I have S songs. So in this case, I will like to have each user stores what? 8. We have 8 users, so S songs. So 1/8 would be the number of songs that each user needs to store without robustness, if it's completely fair. And if I want each songs to be stored at 3 of them, then this will be the number. Now, I don't know what will be the songs. I don't know which users will be online and offline at the same moment. And I need a way that a user can, that if I want to find a specific song, you'll tell me which of the 8 disks I am going to seek this song. So I'll send him a message and ask him, are you online? Can I download the song from you? And I need to know who has this song. And hashing suggests a universal solution to it. So how are we going to do it? By the way, if you didn't take this course with me before, anybody realize the reference here? Reference? Sorry? Pigeonhole, yes, but sorry, TV reference. Of course. Oh, of course. So what do I do to solve it? Okay, if you haven't seen it, yes, so think about hash function, age1, age2, and age3. 3 hash functions. And now a new songs appeared. Here my hash function will just spit out a number between 1 and 8, 0 and 7, sorry, 0 and 7. So each one of the songs. So I'll have 3 hash functions. For example, very simple example. I'll take age1 of k to be 3 times k, modulo 8. Always modulo. Why? Because we need a number between 1 and 8 or 0 and 7. And age2 of k will be 5 times k, and a3 of k will be some other constant times k. 3 hash function. And I publish in Java, and all a user that joins, or the only part that I need some central intervention about all of it, is to decide what are the hash function and publish it among all the users and among future users. All they need to know are what are the constants or what are the hash function, because now everything is known. Because now when I want to insert a new song, at which hard drive will I insert it? I'll insert it. I'll take the name of the song. K will be the name of the song over here. K is the name of the song. Age1 of k will be one of the 3 hard drives that I'll store this song. If age1 of k is 0, then I'll store the song in this hard drive. Age2 of k will be another hard drive. Age3 of k will be another hard drive. Am I sure that it's absolutely fair? No. It could be that some users is very likely to store more songs than the other. It's not total fairness. But it is likely if you have a lot of songs that one of the hard drive will get significantly 10 times more than another hard drive. Very unlikely if your hash function does what it needs to do. Age1 of k has the same chance to pick each one of the 8 disks, the same for age2 of k, the same for age3 of k. Okay, now when you are searching for this song, what are you doing? You when you search for the song, you are getting the value of age1 of k. You are computing which hard drive it is, or what's the IP of the user that supposedly have it, and you send this user a message. Can I get the hard drive from you? The user, let's say it's 0. The user search for the song. If maybe it was deleted. Maybe it was the user is offline. Maybe the specific track was deleted. Anyhow, after a while, you didn't find it on the first hard drive. Then when you search, you will compute what is age, replace the 1 by 2, age2 of k. Age2 of k. Another hard drive sends a message to this IP, or and so on. That will be the second place that you're searching for it, and the third place you're checking for it. So you hit all your goals, and you definitely need randomness in here. You don't need to know what are the songs ahead of time, what are the students ahead of time. You still have the fairness. It's very likely that every hard drive will store, this will be the, it will be store roughly this number. You'll get fairness. You'll get robustness. To destroy the song completely, it needs to be that 3 specific hard drive will be destroyed. Right? It gives you very good resilience to failure. And yes, of course, on top of it, of course, you can put where in the hard disk I am actually storing it, but that's orthogonal to it. Okay, so that's where hashing is so useful for a distributed data structure. Okay, let's start. When I'm discussing hashing, especially in 445, somehow the dot product gives hard time, and I'm not sure why. But at least I try to explain it as well as I could. Most hashing are really excel really significantly if your keys are not just a single number, but a sequence of numbers, a string, a vector of numbers. And in this discussion, when I'm discussing vectors here, I just think about a vector as a list of numbers. It doesn't have, at the moment, geometric setting. When I think about k and I'll put the vector sign out of it, it will just be a list of numbers. If I'm going to hash the string BDCZ, I don't make a single number out of it. Instead, I'll think about it as 4 different numbers. For example, the ASCII value of each one of them. The ASCII value of B is 66, the ASCII value of capital D is 68, and so on. So these will be the numbers that I'll take the key and break it into K1, K2, K3, ... KL. That would be to break K into characters. We'll see soon that breaking them into exactly characters of 8 bytes is not necessarily the best we can do, but for the explanation so far, let's stick with this. You have a string, break it into individual characters. What will be your hash function? Your hash function earlier was to pick one constant A. I'm not doing it anymore. I'm not picking one constant A. Instead, I will pick a sequence of constants A sub I. Pick a sequence of constants. Maybe it's very long. Maybe you want to pick only 10 and do a round robin between them. That's fine. That is that A10 is A1 and so on. And now, what is age of K? K now became a vector, a list of numbers, maybe lots and lots of numbers, but a list of numbers. A, instead of being a single constant, it's now a vector, right? A is a list of numbers, ordered list. By the way, this type of parenthesis means I do care about the order of these numbers. It's not a set where I don't care about the order. And age of K is just take the first character, K1, multiply by the first constant, A1, plus A2 times K2 plus ... up to the last constant, AL, KL, multiply all the individual characters by their own constants, and now we're getting some huge number as a summation. Do of all of it mod M, and this is what we called the dot product method. Why is this a dot product method? Because all we did was to take the vector A, think about it as take the vector A, multiply by the vector K, all of it do mod M. Dot product just take the first times the first plus the second times the second plus forth on. And this is, to start with, that's a really good hash function for long keys. And later we will see that it's not a good hash function. It's actually a fantastic hash function. And we'll see how should we pick the AI. It will actually not be a single hash function, but it's a family of various different hash functions that has a lot of great properties. Namely, It will be a universal family of hash functions. That's what we'll discuss Wednesday. Okay, questions? You look disappointed that I'm a bit ahead of time.